Hello everyone, I am Shubhangi Bandyopadhyay representing my team Synovia. Today I will be presenting our project on Smart AI Traffic Management System. Our project focuses on advancing the existing traffic management system. The major challenge with the current traffic control is that signals are preset and manually operated. Situations like accidents, heavy congestion, or disruption due to weather or festivals require traffic police intervention, which can be slow and inefficient. To address this, our system AI Vista is designed as an adaptive intelligent traffic management system. It uses sensor data and IoT devices to predict and manage congestion automatically. While most cities rely on CCTV cameras, but they are cost effective, have coverage limitations, and struggle during foggy or low light conditions. AI Vista overcome these issues by providing a smarter, cost effective, and adaptive solution. Our project mainly work in two layers, the lower layer or the crossing level and the upper layer or the area level. At the lower level, instead of relying on the CCTV cameras, we install sensors like acoustic sensor, weather APIs to detect congestion. Each traffic signal intersections collect real-time sensor data, which is processed using a time series algorithm that predict congestion by analyzes the last 2 to 3 hours of traffic data. For synchronized lane level prediction, we used RNN generating local traffic insights. This data is then sent via edge devices as input to the upper or the cloud level. At the upper layer, the AI agent, through reinforcement learning, tries to understand the overall traffic condition in that area. It predicts the future traffic pattern for the next few hours, taking in account the data from past 6 to 8 months. For long-term sequential prediction, we use LSTM models, enabling the system to optimize traffic flow across the entire area. Now we come to the solution part. First is our real-time traffic monitoring. We use acoustic sensors for sound wave detection and IoT devices for weather and air pollution check. The system dynamically adapts signal based on environmental condition and special events. Next is the congestion detection and prediction. Lane-wise vehicle counter collected from the sensor. Using time series forecasting and reinforcement learning, the system predicts short-term congestion in the local level and generate the bottleneck alerts. It continuously refines the prediction for better traffic flow. Next is the adaptive signal control. An AI-based signal optimizer adjusts green time dynamically and synchronizes signal along the corridor. Special priority is given to emergency vehicles and public buses. Next, we come to emergency vehicle management. The system detects the siren sound and instantly creates a green corridor, reconfiguring signal in real time with zero delay. The siren sound can be of ambulance or some fire truck. Next is the centralized monitoring and dashboard. This is the UI of our system. The operator can view the heat maps, signal states live, and predictive congestion alerts. The dashboard also allows manual overrides, integrates incident responses, and log data for analytics, trend analysis, and urban planning. Next, we come to the technologies we use. Our system's front end uses React.js with Tailwind CSS for a responsive UI, Plotly for interactive congestion charts, and Leaflet.js for live traffic maps or the heat maps that will be displayed on the dashboard. On the back end, we use the fast API that ensures low latency communication, Kafka for real time event streaming, and PostgreSQL that stored the traffic data efficiently. We collect sensor data from the acoustic and magnetic sensor to detect the vehicle count, cues, and that traffic cues like sirens or fire truck or ambulance, weather APIs, rain sensors, and air quality sensors that provide context aware input. Now, from this data, collected data, we are going to predict the traffic congestion of the area. In the local level, we use the ARIMA for the time series forecasting. It's a ARIMA is handling the short-term forecasting. RNN learn lane level sequence. LSTM modules predict the long-term corridor patterns, and temporal CNN detect anomalies. Installing such sensors, we need a proper battery backup. For that purpose, we use Leon that ensures 4 to 8 hours of backup for keeping the traffic sensing and emergency routing uninterrupted. Finally, all the services are Dockerized and deployed on AWS for scalable, reliable operation. Next, we come to the feasibility and the viability. Our project does not aim to replace the existing traffic management system. Rather, it focuses on enhancing it using AI and smart sensors. First is the technical feasibility. We use an edge to cloud ML pipelines. At the edge level, the sensor to collect, store, and process data locally and then send it as an input to the cloud layer. This reduces the cloud latency, improve efficiency, and allow faster decision making. Next is the economic feasibility. We employ cost-effective, low-maintenance sensors such as acoustic sensor, weather APIs, optical range sensors. These are very much affordable and easy to maintain in comparison to the CCTV cameras. Next is the dashboard and visualization. Our web page based geo-visual dashboard provide real-time congestion heat map, auto emergency corridors, and monitoring tools, making the system simple and intuitive. Next, we come to the viability. First is the sensor first approach. The system prioritizes sensors like optical rain sensor, weather APIs, air pollution sensors like PM 2.5, PM10. These sensors directly detect the congestion through environmental and air quality data. These are easy to deploy. Privacy is also maintained unlike CCTV cameras, intelligent and low cost. Next is the infrastructure compatibility. Our approach enhances existing traffic infrastructure without replacing it, ensuring smooth integration with the current system. Lastly, we have scalability. Using the Edge Cloud ML pipeline, we enable junction to city wide orchestration. Edge devices handle the local processing and generate sequential prediction, which are sent to the cloud for overall traffic optimization. This approach ensures efficient, reliable, and scalable traffic management. Next, we come to the challenges. First is the calibration risk. Sensor accuracy can degrade over time. Continuous operation for several months may reduce the precision of the data collection. To address this, periodic recalibration and adaptive ML corrections are required. Next is the acoustic sensors limitation. Acoustic sensors are noise sensitive, weather affected, short range, and prone to false positives. In a very noisy environment, due to loudspeaker or some other sources, this sensor may fail to detect the sound wave accurately. Next is a capex constraint. Although our sensors are cost effective, the upfront cost of citywide deployment may be a barrier for smaller and low budget cities. Retrofit costs can be significant when scaling. Next is adoption and institutional resistance. Introducing a new AI based system may face policy training and trust hurdles. Authorities need to understand, trust, and accept the system, which requires stakeholders' engagement and alignment with the existing policies. Next comes the risk. Risk is like the budget limitation, calibration drift, slow institutional uptakes, which could overall affect the effectiveness and stakeholders' confidence. Next, we come to the benefits of our solution. Why should one opt for it? Our system has significant social impacts. First, it helps to reduce the travel time, making commuting faster and smoother. It also improves the emergency response efficiency as automatic green corridor allow ambulances, fire trucks, and police vehicles to move quickly. Road safety is enhanced through real-time monitoring, reducing accidents, traffic violation, and rash driving. Overall, it provides public convenience with fewer delays and less stress, improving the urban mobility. On the economic side, AI Vista contributes to fuel saving as reduced idling at signals lower fuel consumption. It boosts productivity since less time is wasted in the traffic, giving people more hours to work. The system also leads to cost saving for both the government and citizen with smoother traffic flow, reducing the maintenance cost and logistic delay. Finally, it can attract investments as a smarter mobility infrastructure makes a city more competitive and appealing for business. Our system also has significant environmental benefits. By reducing the idle time at the signal, it helps lower emission, cutting down of carbon dioxide, nitrogen oxide, and particulate matter. This contribute to sustainable urban development and support eco-friendly smart city initiatives. For a government's and institutional perspective, AI Vista enhances traffic policing with AI-driven congestion heat map and alert that aid enforcement. It also ensures transparency, accountability, as all decisions are data-driven and audit log are maintained. Additionally, it aligns with smart city initiative, integrating seamlessly with existing digital governance and mobility solution. Finally, we now compare our AI Vista with the existing system projects like Vincura AI, Onyx AI, Sarthi. These are the different smart traffic management system implemented in different part of India. Most of these systems rely primarily on the CCTV data and use advanced machine learning algorithms to achieve fast and accurate prediction. However, our approach goes a step further. While we also use effective prediction model, we focus first on effective sensors such as acoustic sensor for sound detection, weather sensor and pollution sensors. These sensors make our system more productive, reliable and context aware, enabling better traffic management in real world conditions. Looking ahead, there are few areas we plan to improve. First, acoustic sensor may not work effectively for vehicles that run on CNG or other low noise engines. Currently, AI Vista is focused on urban congestion detection, and in future, we aim to explore additional methods to address this limitation. Secondly, acoustic sensor can be affected in noisy environment. To overcome this, we plan to implement sound filtering techniques that remove irrelevant noise while accurately detect the siren sound, emergency vehicle signals, and engine pitches. This will make the system more robust and reliable even in high noise urban areas. In conclusion, AI Vista offers a smart, adaptive, and in cost-effective traffic management solution. By combining effective sensor, real-time data, and AI-driven prediction models, it optimizes traffic flow, improve road safety, support emergency response, reduces emission, and enhances the overall urban mobility. Compared to the existing system, our focus on sensor first, context aware intelligence makes AI Vista more productive, scalable, and user friendly. With future enhancement to handle low noise vehicles and noisy environment, the system has the potential to become an integral part of the smart city infrastructure, improving both social and economic outcomes. Thank you.